Hello and welcome to this lesson on random variable. I'm Mohamed Kadem Kahi. The PDF of the lesson is available at the website I indicate here. The outline of the lesson will be firstly to define a random variable, then to introduce expectation and variance. The third section concerns independence of random variables. Then I will present Bernoulli and binomial random variables. In the last section, I will show you the law of large numbers. Let's begin by defining a random variable. Throughout all this lesson, we assume given a probability P on a finite set omega. Remind that this means that P is a function from omega to the interval 0, 1. Remind also that omega is called the universe for the probability. Now, a random variable is a function which we denote capital X from omega to the set of real numbers. It is as simple as that. A random variable is a function from the universe to the set of real numbers. Let's denote by x1, x2, xm the values taken by the random variable x, or by the function x. In this case, we denote x, capital X, equal lowercase xi, as the set of omega within the universe such that the value of the random variable equals xi. So keep in mind this notation when we denote a random variable x equals xi means the set of elementary events in our universe such that the value of the random variable for this elementary event equals xi. The probability law of a random variable x is indeed defined as the collection or the family of the probability of x equal xi for any I. So the collection of all these values will be called the law or the probability law of x. And sometimes we will say shortly the law of x. Here is first a theorem for random variables. The sum over all I of the probability of x equals xi equals 1. Here is a first example of random variable. Remind the experiment of rolling a dice where we introduce the universe to be the set of integers between 1 and 6, and we consider the uniform probability on this set. The probability of each elementary event equals 1 over 6. Let x be defined on this universe as a random variable such that x of omega equals 1 if omega is even and minus 1 if omega is odd. This is indeed a random variable with values within minus 1, 1, and its probability law is the probability that x equals 1 is 1/2 and the probability of x equals minus 1 is 1/2. Here is a second example. Let omega be the set of numbers minus 1, 0 and 1 and define the uniform probability on this universe. Let y be a random variable defined by y of omega equals y squared. This is a random variable with values within 0 and 1. So 0 corresponds to the value of omega equals 0 and 1 corresponds to these two values of omega. The probability law of this random variable will be the probability of y equal 0, which corresponds to this value of omega, is 1/3, and the probability of y equals 1, which corresponds to these two values of omega, will be 2/3. So this is the law of the random variable y. We shall now introduce the expectation and variance of a random variable. So we begin by defining the expectation. Consider a random variable x. Its expectation is defined by the sum over all the possible values of the random variable x multiplied by the probability that the random variable x equals the corresponding value. This is the same value here. And you sum over all the values of the random variable x. The expectation is denoted e square brackets x. So we read this expectation of x, or e of x. So keep in mind this very important definition. The expectation represents the average of the random variable x. Here are the first properties of this expectation. Let x and y be two random variables. Then the expectation of a constant a multiplied by x plus b equals a expectation of x plus b. Moreover, the expectation of the sum of two random variables equals the sum of the expectations. We say that expectation is linear. Let's give an example now. We continue the previous example of dice rolling, where we introduced a random variable x, which equals 1 when the result is odd, I think. I don't remember. I go back to the previous slide so that you see it. Yeah, x equals 1 when the result is even, and equals -1 when the result is odd. So this is our random variable. Let's try to calculate its expectation here. So remind that the law of this random variable is the probability that x equals 1 equals the probability that x equals -1, which is 1/2. So the expectation of this random variable is 1 multiplied by the corresponding probability plus -1 multiplied by the corresponding probability. And since these two probabilities equal 1/2, this expectation equals 0. So keep in mind that the expectation of a random variable represents its average, or its mean. Let's now introduce the notion of variance of a random variable. It is denoted var of x, and it represents the expectation of the difference between x and its mean squared. The standard deviation of the random variable, denoted sigma of x, is defined as the square root of the variance of the random variable x. And this quantity here evaluates how much the random variable x deviates from its mean. So keep in mind also that the standard deviation represents how much the random variable is far from its mean. Now here are the basic properties of the variance. Let x and y be two random variables and a and b be two real numbers. Then the variance of ax equals a squared variance of x. So keep in mind that when you get some number outside the variance, there is a squared here which appears. Now, the variance of a random variable x plus a constant b equals the variance of x. So adding a constant to a random variable does not modify its variance. Here is an example continuing the previous dice rolling experiment. So remember that we considered a random variable x with these two values and this law here. Let's now calculate its variance. It is given by this formula. But remind that the expectation of this random variable is 0, so we get the expectation of x squared, and since x squared equals 1, this is the expectation of 1, which equals 1. Then the standard deviation of this random variable equals 1. So observe in this example that the random variable x has an average value which equals 0, since it takes values -1 and 1 with the same probability. Moreover, this random variable deviates from its mean by the value 1, which is given by the standard deviation. Here now the statement of the Koenig-Huygens formula. It says that the variance of a random variable x may be calculated either by the formula which is given in the definition, or alternatively by the following formula: the expectation of x squared minus the expectation of x squared. Now that the two number here is within the brackets in this first term, and it is outside the brackets in the second term. So the second term is the mean of x squared. Let's now prove this formula. So we calculate the expectation of the difference here squared, which is the expectation of this term here. So we develop this difference squared by the famous known formula. Now we decompose this expectation using linearity, so we get the expectation of x squared, then the expectation of this product here, which gives the expectation of x multiplied by this constant here, expectation of x, and finally the expectation of a constant is itself. And you see here that there is one expectation x squared which simplifies, and we get the desired formula. So we can add the brackets here to emphasize on the fact that the expectation of x here should be taken first, and then we take the power 2 to this quantity. Frequently, we have to calculate the expectation of a function of a random variable. And this is the formula which permits to calculate such expectation. The expectation of a function f of a random variable x equals the sum over all the values of the random variable of f of xi multiplied by the probability that x equals xi. In particular, if we have to calculate the expectation of x to the power of k, it equals the sum of xi to the power of k multiplied by the probability that x equals xi. So keep in mind these two very important formulae. The following section is about independence of random variables. So two random variables x and y are said to be independent if the probability of x being equal to xi and y being equal to yj equals the product of the probabilities. The probability that x equals xi multiplied by the probability that y equals yj. The interest of this notion of independence is in particular to get such formula. If we have two independent random variables, then the variance of the sum of these two random variables equals the sum of the variances. Variance of x plus variance of y. So remember that this formula is not true in general, but for independent random variable this holds true. We generalize this for any number of random variables. So consider x1, xn independent random variables. They are said to be independent if the probability of their values, they've taken some values, equals the product of the probabilities for any possible values of these random variables. And as a consequence, if x1, xn are independent, then the variance of their sum equals the sum of their variances. One of the famous random variables is the Bernoulli random variable. Let x be a random variable with values in 0, 1, such that the probability of x equals 1 is p, and the probability that x equals 0 is 1 minus p. Then we say that x is a Bernoulli random variable with parameter p. Here are the basic properties of this random variable. Its expectation equals p, and its variance equals p multiplied by 1 minus p. Let's prove these results as an exercise. So the expectation of the random variable equals its first value multiplied by the corresponding probability, plus its second possible value, which is 0, multiplied by the corresponding probability, and this gives 1 multiplied by p, plus 0 multiplied by 1 minus p, and this gives p. Now, the expectation of x squared equals 1 squared multiplied by the probability that x equals 1, which is p, multiplied by plus 0 squared multiplied by the corresponding probability that x equals 0. And this gives 1 squared multiplied by p, which gives again p. So by the Koenig-Huygens formula, the variance of x is given by this difference between the expectation of x squared minus the expectation of x squared. So this gives p minus p squared, which gives the stated property here, that the variance of a Bernoulli random variable is given by p multiplied by 1 minus p. A second famous random variable is the binomial random variable. It is defined as follows. Consider xn, x1, xn independent Bernoulli random variables with parameter p. Then their sum, x equals to x1 plus xn, is called binomial random variable of parameters n, p, n being the number of elementary random variables and p being their common parameter. Here are the basic properties of this binomial random variable. Its expectation is given by n multiplied by p, and its variance equals np 1 minus p. Here is the proof of this result. The expectation of x is the expectation of the sum here, which is by linearity of expectation the sum of these terms here. But each of these terms equals p, so we get finally n multiplied by p. Now, since x1, xn are independent random variables, then the variance of the sum equals the sum of variances, but each term here equals p multiplied by 1 minus p. So finally, we get n times p 1 minus p. We aim now to give the probability law of a binomial random variable. To this end, we introduce this notation. Factorial n equals 1 times 2 times n. And moreover, for any k within 0n, we define the binomial coefficient, denoted like this, nk, as factorial n divided by factorial k factorial n minus k. And indeed, this is the number of subsets of size k in a set of size n. Sometimes we denote this also like this, binomial coefficient cnk. This is the same notation. Observe that in these two notations, the places of n and k are inversed. Okay. The following theorem gives the probability law of a binomial random variable. So let x be a binomial random variable of parameters np. Then its probability law is given by, for any k within 0, 1, n, like this, we have that the probability that x equals k equals the binomial coefficient nk multiplied by p to the power k 1 minus p to the power n minus k. So keep in mind this very important formula for the binomial random variables. Let's prove this formula. The event x equals k occurs when k variables among x1, x2, xn equal 1 and the others equal 0. Since in this case the sum of these random variables will give the value k. Observe that there are the binomial coefficient nk ways to choose k variables among x1, x2, xn. Moreover, for each of these choices, the probability that the k variables chosen are equal to 1 and the others equal 0 is p to the power k multiplied by 1 minus p to the power n minus k. For example, the probability that the first k random variables equal 1 and the other ones equal 0 equals p to the power k, which corresponds to this term, multiplied by 1 minus p to the power n minus k, which corresponds to this term here. So finally, we get that the probability law of the binomial random variable is given by the expression stated in the previous theorem. The last part of this section is about the law of large numbers. Before stating this law, we need some inequalities. Firstly, the Markov's inequality, saying that for any random variables with non-negative values, the probability that the random variable exceeds some value t is smaller than expectation of the random variable divided by t. Then we have the Chebychev's inequality, which may be deduced from the Markov's inequality. It says that for any random variable x, the probability that the difference between x and its expectation in absolute value exceeds t is smaller than the variance of x divided by t squared. The Chebychev's inequality implies what is called the concentration inequality. It may be stated as follows: let x1, xn be independent random variables with the same probability law and with expectation mu and variance v. Denote the mean random variables mn as 1 over n multiplied by the sum for I equals 1 to n of xi. Then the probability that this random variable mn minus mu exceeds t is smaller than the variance v divided by n times t squared. And from this concentration inequality, we can now deduce the famous law of large numbers. It says that if x1, x2, etc. is a sequence of independent random variables with the same probability law, with expectation mu and variance v, then the probability that mn minus mu exceeds t, this probability converges to 0 as n goes to infinity. And this means, indeed, that mn converges, in the sense given here, to mu as n goes to infinity. Here is a particular case of the law of large numbers. It says that if x1, x2, etc. is a sequence of independent Bernoulli random variables with parameter p, Denote Sn, the sum for I equal 1 to n of xi, which is a binomial random variable of parameters np, then the probability of the ratio Sn divided by n minus p in absolute value is larger than t. This probability goes to 0 as n goes to infinity. And this precisely says that Sn divided by n converges to p as n goes to infinity. So the interpretation of this result is that if we repeat a random experiment a large number of times, then the frequency of an event converges to its probability. This is a very useful application of the law of large numbers. Okay, this ends this lesson about random variables and the important theorems for these random variables. I hope it was clear and useful. See you in the next lesson. Goodbye.